Okay, so far we've dipped our toe into thinking about what buffers are, their utility, and a little bit of how to compute them. But we're going to move and add a little bit more generalization to those things by thinking about this thing called the Henderson-Hasselbalch equation. So remember, a buffer is really simply defined as just a mixture of a weak acid and its conjugate base, HA and A minus. So we can think about the generic dissociation of HA into its conjugate base up here. We could write out an equilibrium expression for that, which we've seen a million times now. It looks something like this. But when we're thinking about the utility of a buffer, then we're really thinking about its pH or its resistance to pH. And so if we want to think about that fully, we should just rearrange this equation in terms of H3O plus, because that really is what pH. And that gives us the sort of generic form or the starting point for this thing called the Henderson-Hasselbalch equation. And the way we can sort of think about this intuitively is a buffer contains both HA and A minus, and its capacity or ability to resist pH really just comes from this part of the equation. So if this is pH, or it almost pH, negative log of that is the pH, and this is a constant, then really all we're changing in a buffer is the ratio of the conjugate acid to the base. That's it. And all we're going to do is sort of take the log transform of this so that we're actually talking about pH and not H3O plus. That's all that the Henderson-Hasselbalch equation is. It's the thing you already know. It's the equilibrium expression for the dissociation of HA, but it's been transformed by a log. So in other words, the Henderson-Hasselbalch equation here, which I'll just write as HH equation, it's really simply just the log transform of this expression, which we've already known and talked about a million times so far. So I'm going to just quickly walk you through that log transform. It doesn't matter if you remember the process. I just want you to know that the Henderson-Hasselbalch equation, which you use a lot in this class and a lot in other classes like biochemistry, is nothing fancy. It has its own name, but it almost shouldn't have its own name because all it is a log transform of something you already know, which is the equilibrium expression for a weak acid. Okay, so let's start with a fresh white sheet here, and let's just take negative log of both sides of this equation. So that just looks exactly like you'd expect. It looks like that. And what's convenient is we already know that negative log of proton concentration is pH, so we can just write that as pH. And at the same time, then I'll just expand or factor in this log term here on the right side of the equation. That gives me negative log Ka, and then our log rules here. Oops, that shouldn't be a negative. Minus log of the HA over A term. And you might be able to spot a simplification here, which is that negative log of Ka is pKa. And so we are converging on our final form here, which when fully simplified is just pH is equal to pKa plus log A minus over HA. And so the plus just comes from flipping the numerator and denominator, and with a log term, then that just flips the sign of this thing. You could equally leave this as pKa minus log HA over A. That would give you the same answer. But this is the Henderson-Hasselbalch form of the equation. Okay, so hopefully this isn't that daunting to you now, because really it was the original form that we've been working with in this entire class, and all we did was take the negative log of both sides. That's it. And really it's just a convenient form to work in because we're often thinking about things in pH and pKa. So what are some of the implications of this, or how can we look at this and maybe understand how pH is related to weak acid and conjugate base concentrations? Well, first thing we can do is we can interpret that the pH of a system that contains a weak acid and its base is really just the pKa of that system modulated by this term, or the ratio of those two things in solution. In other words, you can sort of think about this term as a dial, because you have control over this. You can control what the ratio is. The pKa is a constant, and since you can control this ratio, then that means you can dictate what the pH of your solution is, simply by modulating what those are. Another sort of convenient sort of mathematical outcome of this equation is that what happens when you have equal parts of your base and your acid? Well, that term becomes 1, log of 1 is 0, and now the pH is simply equal to the pKa of the system. That's a really nice outcome. Another mathematical outcome here is what happens when you say you have a system that's like 10 to 1. Well, log of 10 is just 1, which means that every factor of 10 change that you have in the ratio, you get 1 increase in pH unit from the pKa. So if we have 10 times as much base as we do acid, then the pH is going to be pKa plus 1. Similarly, we could flip this and write this as 10 times as much acid as base in this system. And now log of 0.1 is -1, which should be intuitive. And so if the ratio is flipped here, now we have a pH that's equal to pKa -1. Similarly, this could be 1 over 100. Now that becomes -2. 1 over 1,000 becomes -3, etc. And so it's a really convenient way to quickly understand what the implications of this ratio term is on the pH of the solution. One final implication here, which is really important to realize, is that the pH of a buffered solution does not depend on the volume. So for example, we have a beaker, and let's just say there's a liter in there, and we have HA and A minus in there. If we were to dump in another liter of pure water, and now we have 2 liters, what about this Henderson-Hasselbalch equation changes? Well, nothing, because the concentration of these two things would decrease by half because we are doubling the volume, right? We still have the same number of moles, but now twice the volume, so the concentration halves, but both of them are affected at the same time, which means the ratio itself is preserved. Nothing changes. So that means I can add 1,000 liters of water. And if I keep adding water, the ratio of these two things still doesn't change. And so it's independent in volume, generally speaking. Of course, you could dilute this thing so much that the concentration of H plus from water is then, which is 10 to the minus 7, if that exceeds that of the concentration of H plus from your HA, then you have a problem where you've just diluted the whole thing, and the whole thing has a pH of 7. But generally speaking, buffers are independent of concentration.